My name is Ravi Babu, Assistant Professor in Institute of Aeronautical Engineering College. Yesterday class we will see the mapping between the S-plane and jet plane. Why are going to this mapping between S-plane and jet plane? Nothing but we have to analyzing the any characteristic equation or any system stability condition. Why? Because in stability condition we have to assign the poles and zeros or in S-plane in case of the linear time invariant systems, in jet plane in case of the discrete time systems. Now we are going to moving the stability condition. First of all, what we mean by stability? Stability nothing but for a given system, if you apply the bounded inputs, if you get the bounded outputs, then the system is stable condition. Otherwise, for a given system, any system, if the output is followed by the input with linearly, then the system is called as a stable system. So now we are seeing the in this topic, it is introduction of the stability, asymptotic stability, Bibo stability, internal stability, and Routh-Hurge stability criteria for discrete time systems, and for jury stability test. Jury stability test. Coming for the introduction part, that is generally the stability is a basic requirement for digital and analog control systems. In case of the digital control system, is based on the samples and is updated every sampling period, and there is a possibility that the system will become unstable between the updates. This is absolutely make that the stability analysis is different in the case of the digital case. That is nothing but in case of the digital system, we are getting as a sample periods like this. If you take a square wave, this sample period, it is going to be analyzing. We have to take the analyzing for this one. It is sample periods. So there is a different definitions and tests of the stability for linear time invariant systems of the digital systems based on the transfer function. That is, if the input and output stability and internal stability, depending upon the transfer function, we are to analyzing the input output stability and internal stability. Next one is we have to also analyze the system with RH criteria, low stability criteria, and also we are having the for finding the stability conditions, we have the jury stability and Nyquist criteria. Coming for the last one, that is phase margin representations. In that one, we are having the gain margin and phase margin representation for digital systems. That is Bode plot and Bode plots. That is nothing but Bode plots and root locus. We have to representing the stability conditions. Coming for first one, asymptotic stability. Generally, the asymptotic stability is nothing but it is the solution of the where the system is taut and close enough to remaining closed enough, but actually it is in the coverage of the equilibrium. That is the most commonly used definition of the stability are based on the magnitude of the system response only in the steady state condition. Why? Because in case of the transient state conditions, it is not possible to the finding the stability condition. That is, we have to mention the in case of the transient state conditions, we have to apply the lower and upper limits for the every time of the variations. There is no possibility for finding that one. So in case of the steady state condition only, we have to making the stability conditions. We have to mention if a steady state response is unbounded, then the system is going to be unstable condition. So for definition of the asymptotic stability, that is nothing but a system is said to be asymptotically stable if its response to any initial conditions decays to 0. Decays to 0. That is nothing but it is considered as a under stable condition. If the response is due to the initial conditions remains bounded but does not decay to 0. That is nothing but it is called as a marginally stable. That is, in case of the jet plane, you have to remember that in last class I explained that in case of the jet plane, we have to taking the unit circle. That is, if the poles or zeros are representing within the magnitude section side, if it is within the magnitude, nothing but it is a unstable. It is a stable. Or if it is in the circle, unit circle, on the unit circle, it is called as a marginally stable. If it is a out of the circle, it is called as a unstable condition. Coming for here, for explanation of asymptotic stability, in case of the linear time invariant systems, if you representing here, it is a unit circle range area. If the radius of this one is 1, that is, I am taking the disk with radius 1. So, in the absence of the pole zero cancellation method, in linear time invariant system, digital systems is asymptotically stable if its transfer function poles are in the open disk, and it will be marginally stable when the poles are in the closed unit disk. That is, it is not repeated on the unit circle. It is not repeated on the unit circle. That is, in this place. In this place, it is not repeated. It is not repeated on the unit circle. Okay. Whenever we are saying is that the magnitude will be equal to 1 only. That is, the open loop unit disk as a region, the complex plane defined as where the region of the z, magnitude z is within the unit circle. So, the closed loop unit disk will be region in the complex where we are defined as the, for closed loop, nothing but it is equal, less than or equal to 1. Whenever you are taking the open loop system, that is nothing but the magnitude of the unit circle disk is z less than 1. Whenever you are taking the closed loop disk is in the region that is less than or equal to 1. So, I am here considering an LTI system governed by the difference equation, that is y of k plus 1 plus a power of n minus 1 into y k plus n minus 1. So, with the linear integration of the degrees as a1 into y of k plus 1 plus a0 into y of k equal to bm into u of k plus m plus bm1 minus 1 into u of k plus 1 m minus 1 plus up to so on. Where here y is the initial conditions. Y is the initial conditions. Y is the nothing but it is the output of the system. U is the input of the system, and we are in the at the center as a state variables, that is x of the systems, making the initial conditions, that is y naught, that is nothing but output of the system at initial condition. Okay, after one decay it is coming to as y of 1. Okay, so I am considering it is up to y of n minus 1. Now I am going to taking the z transform of the output response, that is y of z. If I am taking this total part equal to n, this total part equal to n, so n of z by z power of n into a minus 1. See this one, a minus 1, okay, up to an, okay, and a1 z1 like this. Okay, it is coming to as this one. That is, it is a output function, transfer function, where n of z is a polynomial dependent on the initial conditions. Now, taking the transfer function, because the transfer function zeros arises from the transfer function of the point input section side, so we are going to influence the response due to the initial conditions. So, coming for here, the input term, we having the no influence on the response due to the initial conditions. the input term, that is n of z, it is not having any initial conditions. The denominator of the output z transform is same as that of the denominator of z transfer function. Okay, in the absence of the pole zero cancellation methods. We know the pole zero cancellation method in control system method. Okay, hence the pole zero function of the y of z is the poles of the system of the transfer function. So finally we say that the output is going to be as the initial conditions for bounded of the systems poles on the unit circle of the disk, close to the unit circle of the disk, with no repeated poles on the unit circle. No repeated poles on unit circle. Remember that one. So asymptotic is stable, nothing but the magnitude of the system is, okay, if you take any system mod z is less than 1, then only it is the asymptotic stability. Simple, sir. That is nothing but inside the unit circle only. Unit circle only. That's why this third point. The output due to the initial conditions is bounded for the system poles in the closed unit disk with no repeated poles on the unit circle. Okay. If any pole, already I explained yesterday class. If any poles are repeated on unit circle, repeated, not different places. At one place only it is repeated. For example, if you take a pole is like this here, another pole is same place. Okay, another pole is same place. That is nothing but it is coming to as asymptotic, marginally stable, repeated. If it is not repeated, that is nothing but asymptotic stable. Asymptotic stable. Okay, so coming for examples here. Take the first one. Whether it is a asymptotic stable, we have to define. So, first of all, assign the poles and zeros in location in unit circle. For first one, z equal to 2. It is pole. Z equal to 2. Again, z equal to 0.1. Okay. Z equal to 0.1. So, it is 0. It is poles. Where is that one? Pole, where is the pole location is? Within the unit circle. Okay. One pole is within the unit circle. That is 0.1. It is unity circle radius. So it is asymptotically stable. Asymptotically stable. Coming for the next one. Here also, it is z equal to 0.2 is one 0. Z equal to 0.2 is the one pole. Z equal to 0.1 is the another pole. So 0.1, 0.2. It is within the circle. That's why it is also will be asymptotically stable condition. Asymptotically stable condition. Coming for the next one. H of z equal to pi into z minus 0.3 by z minus 0.2 and z minus 0.1. Okay. So for this one pole is 0.2, other one is 0.1 and 0 is 0.3. That is all poles and zeros are in within the unit circle. Within the unit circle. So it is considered as asymptotically stable. Asymptotically stable. Okay. Coming for the last one. Here z equal to in numerator part, that is nothing but in pole section, in zero section, z equal to 2, 0.2. And coming for the denominator part, that is in the pole section, that equal to z equal to 0.1 and z equal to 1. Okay, substitute this equation into above 1. So what happened? Z value. So z is nothing but 0.1 within the unit circle. Z equal to 1, that is on the unit circle. Okay, on the unit circle. Okay, so that is nothing but it will be stable or asymptotically stable. Asymptotically stable. Okay, so why? Because this part is nothing but z equal to 1. That is, it will be lie on this unit circle. R equal to 1 radius, it is unit circle. So finally we say that the first 2-3 R examples are the asymptotically stable, and the third one is the asymptotically stable and marginally stable. Sorry. Asymptotically stable. Asymptotically stable condition. Next. Coming for the next one. Bibo stability. Bibo stability nothing but we having the bounded inputs and bounded outputs. Okay. Bounded inputs and bounded outputs. That is the second definition of the stability considering and taking the forced response of the system for bounded inputs. So we consider that one is I am taking the one of the bounded out input satisfaction that comments are k. U of k less than b power of u, where k equals 0 to 1 up to 1 between 0 to infinity. So for a bounded squaring satisfaction, we have the condition that it is uk less than 1. Okay, uk less than 1. See this one condition, uk less than 1 conditions. Okay. So coming for next one. What is meant by bounded input and bounded output stability? Bibo system. A system is said to be bounded input and bounded output stable if it responds to any bounded input remains bounded. That is nothing but if you are taking the bounded 5 input boundeds, then the output also will be coming to 5 output boundeds. That is nothing but the primary system. If you take any system, you having there 3 bounded input elements. If you are getting that one is 3 bounded outputs. Okay, 3 bounded outputs. So what happened? So the output is going to be satisfied as y of k less than by. So where we know that the k values is up to infinity. That is the thing we have to in the bounded now. We are in the bounded. So for bounded input, bounded output systems, considering the response of the system, so the value will be output value will be I equal to 0 to k h into u of k minus I into ready. Okay, that is nothing but where h of k is a impulse response of the sequence system. Okay, impulse response of the sequence of the system. Now, what do you mean by difference between the asymptotic stability and Bibo stability? Generally, in case of the LTA systems with no polo zero cancellation and Bibo and responsive stability are different. Can be invested as using the state some tests. So finally, the stability is used in the internal to donate either Bibo or asymptotic stability conditions with the assumption of the unstable pole zero cancellation. Unstable pole zero cancellation. So this is the basic difference between the asymptotic stability and Bibo stability. Okay, that is we have to consider as it is a unstable cancellation in the pole zero cancellation method. Internal stability. That is nothing but if I am applying here one of the open loop control system stability, I want to consider the system. However, the stability of the system is going to be defined as the for closed loop transfer function proper system. We are mentioning the operation because of the internal variable values. So, in feedback control system, it is essential to that we have to make the signals to loop bounded when bounded exciting inputs only for the applied system. So consider this one for internal stability. Okay, consider the unity feedback digital control system. Okay, this is your digital control system with the unity feedback. That is nothing but the feedback will be 1. So the system is having the 2 inputs. Okay, the system is having the 2 inputs. What is the inputs here? One is the G of Z, one is the R of Z. Okay. So for writing this one, transfer functional system, output y of z, input u of z, that is the first case. U of z equal to first forward path is, okay, first forward path is c of z into gas g of s by 1 plus g of s into g of s into g of s plus g of g2 of as by, so see, this is first one. From here to here, it is first one. First one. Okay. From here to here loop is completed. Next. From here to, okay, gas here to here. Yes. Here to by 1 plus kg by. Okay. This is a kg of s. So this is for 1 and 2, between 1 and 2 for this system. And this is last one is middle third one is, it is for 2 to 1. 2 to 1 nothing but C of output section side, primary section side, C of z by 1 plus g of s into g of s. This one. This one. Okay. And the last one is only for the itself of the self. So what happened? C of z by 1 plus c of z into zds plus c of z into d of s by this value into r of s into d of z. This is your internal stability. Okay. So finally we say that the total transfer functions are may be real to inputs of the system. That is nothing but d into a. Okay. There is a possibility for getting the y also. And this BIBO system is said to be internal stable condition. Internal stable condition. Okay. So these are the references. Now in next class we will see the one of the topic as RH criteria and jury stability system. So we have completed up to here. In this one, you have to complete the introduction part as a total stability, BIBO stability, internal stability. Now, in next class, we will see the RH criteria and jury stability conditions, where it is, remember that one only. In case of, remember that one, if you take it is unit circle, in this one, if I am taking here, it is unit circle. Within the circle, in case of the not LTI systems, in case of the discrete time control systems, it is stable. Outside the circle, unstable. Within the circle, marginally stable. Within the circle, marginally stable. Outside the circle, unstable. Okay, unstable. So you have to remember these three things. And one more thing is there. Upon the unit circle, the poles are repeated. The poles are repeated nothing but unstable. Unstable. Okay. And coming further here, okay, these are the, you have to key points, you have to remember. Okay, one more thing. Take the first of all, if the given function is open loop system or closed loop system, you have to identify. Why? Because in case of the open loop system, okay, whereas asymptotic stability is less than 1, the margin it will be less than 1. Whereas in case of the closed loop control system, less than or equal to 1, remember that one. It is also very important. In case of the asymptotically stability conditions. Asymptotically stability conditions. Okay. These are the asymptotically stability conditions and BIBO system. We have completed this one. In this one asymptotic stable is stable condition. BIBO system, you have to complete this one. For a bounded input, we are getting the bounded output. And the comparison between the asymptotically stable and BIBO system. Internal stability. Okay. See the this one definition. I am taking the to here. Okay. See here. That is nothing but in case of the internal control system, we having the internal transfer function. For that one, y of z output by input is u of z here. Here, u of z. Okay, u of z. You are writing the system functions like this. Next. So internal stability, and these are the references. So we continue for tomorrow RH criteria and some of the problems. After that one, we go for the jury stability test.
Like, share and subscribe. Hit the bell icon for more updates.